then it's not a Cauchy sequence. But at the same time, if a sequence converges, there is this is like this. So if the sequence converges, then it's called Cauchy sequence. So if a sequence does, if a Cauchy sequence exists in a space, in an inner product space, then it's called complete inner product space. So what we are saying here is that a Hilbert space is an infinite dimensional complete inner product space. Okay, then why this is very important? Again, this has a huge application in quantum mechanics. It has an application in stochastic processes, and it has application in the wavelet. These are very important field of engineering. I mean, and these are the in field of physics I like. So that's why I'm more into this kind of stuff. It has a huge application in quantum mechanics. It has an application in wavelet. It has an application in stochastic processes. This Hilbert space is an abstract definition of all the linear transformation we know, like Fourier transformation, for example, is an instance of this Hilbert space. It's an instance of this Hilbert space. And you take Euclidean geometry, Euclidean space, again it's an instance of this Hilbert space. All finite dimensional space are an example or an instance of this Hilbert space. Then the inner product is again an abstraction of the dot products. Like, you know, we studied maybe in middle school, let's say x is a vector and y is a vector. The dot product of x, y is equal to cos theta, right? So this is the dot product of two vectors. Again, inner product is an abstraction of a dot product, right? So since I mentioned this, I want to expand on this orthogonal. See, again, orthogonal. This is all very important concept which we need to know for the future lecture series. Orthogonal is a fancy word for a perpendicular. So let us say there is a two vectors, right? X, this is a vector x, and this is a vector y. And these two vectors are orthogonal if they are perpendicular, right? To generalize this orthogonal concept, if an inner product of two functions is 0, then those two functions are called orthogonal functions. Let's say if f of x belongs to R and g of x again belongs to R, it's a finite dimensional space, then the inner product, what is the inner product of this? Say f of x, g of x, dx. Again, if no, it's not a complex. If it is 0, then f of x and g of x is considered as the orthogonal function. Then the closer the orthonormal function. So let me take this dot product I talked about, right? This x dot y is equal to cos theta. Right? If theta is 90 degrees, then obviously this has become 0. Irrespective of this value, this dot product of these two vectors is going to be 0. So again, we just now saw that a two function or a vector are considered as a orthogonal function or orthogonal vector if the inner product is 0. Again, I mentioned before that the dot product is just an instance of an inner product. So in this case, if this is 0, then x and y are x and y vectors are called orthogonal. Okay, so if a two vectors or a two function is orthogonal and the norm, see again, this is nothing but the norm of the function or the vector is equal to 1, then this x and y is said to be orthonormal. I repeat, if two vectors are orthogonal and the norm of each of these vectors is 1, then it is called orthonormal vectors. And again, the same thing applies to a function. Let's say R and g of x is R, belongs to R. Then these two functions are said to be orthogonal if the inner product of these functions are 0. Then the norm of this function is equal to 1 and g of x is equal to 1, then this function is said to be orthonormal. So if the two function is orthogonal and if the norm of each of these function is 1, then these two functions are said to be orthonormal. Okay, now I'll go back to the joke I was telling in the beginning. So this guy asked his girlfriend that, do you know Hilbert? And the girl says that she doesn't know Hilbert. Then the guy says back that, what are you doing in his space? So the idea is, the joke is that we basically live in Hilbert space. So it's Hilbert space is an abstract definition of Euclidean geometry. It's abstract definition of the Fourier transform. All finite dimensional space are instance of Hilbert space. So it's basically, I hope now you, the people who did not get the joke in the beginning, now they will get the joke. Thank you.